Again, let's consider perhaps the most straightforward change that we could make to a reaction that's at equilibrium, and that is to change its composition. So let me put that down here as a placeholder. All right, now I'll remind you that our hypothetical reaction is as it's been given before. I'll also remind you of a relation that we developed in the first video of this lesson, and that is that delta Rg is equal to RT times the log of the ratio of Q to K. And what I want to do is focus on this ratio. And in particular, what I want to point out is the following. If in this ratio, Q ends up being less than K, then that means I'm going to have log of a number that's less than 1, okay, because Q over K is going to be some fraction. But log of any number less than 1 is going to be a negative number, so that means that delta Rg is going to be less than 0. Similarly, I could argue that if Q became greater than K in this, that would lead to a final result that says that the Gibbs energy change would be greater than 0. Well, what we know about spontaneity is that when Gibbs energy change is less than 0, it's a spontaneous process. Now, the way we will interpret that is it means that the reaction proceeds in the direction that it's been written. When delta G is greater than 0, however, this will be cause for us to believe that the spontaneous direction of the reaction is actually going to be the other direction. That is back toward the reactants. All right, so I want you to bear that in mind as we go through these analyses, and that'll make it a little bit easier for you to see some of the conclusions that I might draw from this. All right, now let's start off by writing down what is Q for a typical reaction like this one. Now I'm going to write this in terms of the activities because that's the most general way that I can write them. All right, and in this case, in terms of the activities, I'm going to have the activities of the products raised to their stoichiometric powers, A times D times raised to its power, divided by the reactants, A sub A and A sub B. All right, so this is perhaps the most general expression that I can write for the reaction quotient, and I say that because in the right limits, these activities could be interpreted as partial pressures, they could be interpreted as pure substances, pure liquids or solids, they could be interpreted as solutions and concentrations of things in solutions. So this is in fact the most general way that we can write this. All right, so now let's see what happens when we begin to change these chemical activities in ways that change the composition. So I want to consider two possible cases. All right, the first case I want to consider is, let's suppose that I increase this one. I'm going to say AC increases. All right, now the first thing we want to ask is, okay, so AC increased, what effect does that have on these other things? Well, if I increase something in the numerator of a fraction, what that means necessarily is that I'm increasing the value of the fraction. So in other words, QA is increasing. Okay, now if I've increased QA, what effect does that have? Well, I started with QA equal to its equilibrium value. So QA was equal to KA to begin with. But now that I've changed it, I'll have a new situation in which QA is greater than KA. So that means when I look at the ratio of the two, so in other words, the final word on the response of the reaction is that QA over K, I should say KA, is greater than 1. So that means that the log of this ratio is a log of a number greater than 1, so this log is greater than 0. So what that means necessarily is that the change in the Gibbs energy for this process is going to be greater than 0. And what do we know about that? It means that the spontaneous direction is going to be toward the reactants. So spontaneously proceeds toward reactants, okay, which is in this direction. Okay, so in this case, when we've added something on the product side of the reaction, the natural direction for this reaction to proceed is back toward reactants, and that it would be in accord with our understanding of Le Chatelier's principle, at least at the level of general chemistry where we've seen it before. All right, just to sort of tie this down, what if instead I increase the A component? So I'll say that the activity of A increases with all the others staying the same. All right, in this particular case, I'm increasing the denominator of Q. So that means that QA is going to decrease. So I went from QA is equal to KA to a situation where QA is greater than, or sorry, less than KA. So that means that the response of the system, the response of the reaction, is that my ratio of these things is going to be less than 1. And that means in turn that the logarithm of this ratio is going to be a number what? A logarithm of a fraction is always going to be less than 0. So now the conclusion that we draw from this is that the Gibbs energy change for this reaction is going to be less than 0, which means that it will spontaneously proceed toward products. Right, so this is, I think, all in accord. Again, if we add more reactant, we'll push the reaction back toward products. If we add more product, we push the reaction back toward reactants. So these are, I think, fairly easy to understand in terms of the basic principles of Le Chatelier's principle. But let me give you an easy mnemonic, or at least I hope it's an easy mnemonic to think of. Let's suppose that I have a number line, okay, and my number line is going to start at 0. You can't go below 0. And on this number line, I'm going to designate where the equilibrium constant is. Now, I'm not going to designate Ka or anything. I'm just going to say the equilibrium constant. We'll understand that K and Q are measured using the same system. All right, so now if my Q is down here, then necessarily I have the condition that K is greater than Q, okay, because K's over here and Q's over here. All right, so that means that Q has got to proceed in this direction. It's got to move toward K. All right, if I had instead my Q was over here somewhere, so it's bigger than K, now my condition is that K is less than Q. And in this case, Q, the reaction has to proceed back toward this direction so that Q can become equal to K again. And once it becomes equal to K, it re-achieves equilibrium. So in a sense, if you list K and Q alphabetically, K comes before Q, then just look at the greater than or less than sign. In this case, it's a greater than sign, and it's pointing to the right. In this case, it's a less than sign, and it's pointing to the left, and it tells you which direction the reaction should go. All right, so this has just been a quick take on this particular aspect of Chatelier's principle. We'll look at some of the thermodynamic changes in the coming video.